it's difficult and you don't need it in this class. You just need to have some common sense. It's all about common sense, right? If you need that, go to computer science and take a class on algorithm complexity. Now, for example, just a fake example. Let's say I want to do addition, right? I do 2 plus 3. Let's say I take 1 second, right? What if I do 22 plus 23? I need to do 2 plus 3 equal to 5, 2 plus 2 equal to 4. I use 2 seconds, right? What if I have n digit? Right? N digit. I'm going to do n digit addition. And you really don't know. I mean, I assume I use the same time for each digit. I assume I spend no time on carry over, right? How much time do I need? 10 seconds, right? So this is like, we call this order of n. This big O, we call it big O, right? It's talking about the complexity of the algorithm. Now, the complexity of algorithm here depends on the number of digits you are doing. Okay, the problem, not algorithm, the number, the size of the problem is the number of digits, right? It all depends on the problem that you are dealing with. This is like I keep increasing the number of digits to do addition. So it's n. So this one go up linearly, right? So if I have 1 trillion digits, it's spending 1 trillion seconds, okay, which is very long. Now, maybe I am smart. I came up with a new algorithm. Okay, I cannot tell you how because I'm not smart enough. I can do this addition in log n second if I have n digit. Okay, for example, if n equal to 1, then there will be a problem, but you trust it. The time I take is 0 seconds. If it's 10 digit, the time I take is 1 second. If I 100 digit, the time I take is 2 seconds, right? What if I have what do you call this? 1 trillion. 12 is trillion, right? 1 trillion digit. How much time do I need to do this calculation? 12 seconds. It's a big deal, a big difference from the linear operation, right? I only need 12 seconds to do 1 trillion digit. This one, we call it an exponential speed up of the original algorithm. But yeah, in terms of this capital, we say this is log n, right? Log 2, log 3, log 10 really doesn't matter. It will give you some offset, some constant. But the orders of magnitude matters. Because I reduce 1 trillion to 12 seconds. Yeah, if you do log 2, maybe it becomes 100 and 1,000 seconds, I don't know. Not a big deal compared to 1 trillion seconds. Okay, so of course in computer science, you have a very detailed analysis. They care about this overhead or this prefactor also. But here we just vaguely say that you should understand some algorithm have the exponential speed up. So here this is an exponential speed up. Over the first algorithm. Exponentially. Because the exponential of this number equals to the original number, right? 10 to the power 12 equal to original 10 to the power 12. Is that okay? And if your quantum computing algorithm can provide exponential speed up, then that would be great. Now, some algorithm is not so great. That is what it does. For 1, it takes 1 second. For 2, it takes square root 2 seconds. For 100, it takes square root 100 seconds. So what is 1 trillion? It takes 1 million seconds. Still not bad, actually, because 1 trillion may be too long for my life. I don't know about what is 1 million. maybe a few years, you need 10 years or something, right? At least I can do it before I die, right? So it's still a speed up. This is a square root speed up, so we say this is in the order of square root n. I still love that, but it's not as good as log n. And of course, there are many variations. It can be n log n. For example, yeah, I don't know how to talk about that. But so, is this okay? Now, if you try to plot this figure, sorry, it's not very well organized here. This is the time, and this is the n. If it is linear, now I'm going to plot in this way, then you understand. You will get something like this. Okay? If it is logarithmic, if it is square root, how will it look like? Be short. And then when it is log, it will be even lower, right? I really don't know how to draw it, sorry. I mean, it need to be lower than the square root eventually. Okay? But usually, if I have a smarter algorithm, when my number is small, you actually have more overhead, right? Usually. Now you can compare this. If you assume you have quantum computing algorithm that give you exponential speed up, you see that it is basically useless for small number because you have a lot of overhead. This including the error correction or whatever. But you will have a lot of advantage if you go to the very large number. Okay?
So, isn't that interesting? Because most of the quantum computers use the high end, but they're talking 50, 60 qubits. So if you were to put that on this curve,
They have no speed up yet. You're right. At this moment. But here I drew it wrong. I still need one more thing. I did not do it well. So this is square root 2, square root n. This is log n. This is n. You see that you compare the square root and the linear one. It actually takes larger n in order to have benefit, right? So for the algorithm that only have square root speed up, you will see that even it is successful, it will take longer time to see it to be useful, okay? Because it has much more overhead, okay? So that's why people hope that mostly try to bet on the log one, but the log one usually also have more error. So God is kind of fair. It's not easy to really get something that is better than the classical one. But I just want you to have this picture, right? The trade-off. First is what is the complexity of the algorithm, right? You can have exponential speed up, you can have square root speed up. But you should understand that there is overhead. This overhead can come from the extra manipulation, data processing, and also due to the error in quantum correction. So you do need a large n, right? So that here I did not draw it well. This one will just keep going up, right? A large n so that you will clearly see that the quantum algorithm takes much less time for computation. Okay? Yeah.
now this might be a computer science. You're looking at the two camps, the long end and square root n. How many algorithms are in each camp? The ones that we've already invented.
Oh, that I don't know. I don't know. So I think some people should have done this type of summary, how many algorithm are exponential, how many are square root, but I did not pay attention to this. Yeah, maybe you can try to Google.